is the topic that we are going to be taking a look at. And what is a binary operation? Well, it may sound very strange to you. However, the binary operations are not really strange because your regular addition, your regular multiplication, your regular subtraction, your regular division are all binary operations. They are binary operations because they are two entities, two numbers, two letters, two symbols on which the operator is operating. And each one of these is called an operand. So that's an operand, and this one is an. So for each of those operations, we have two operands. And when we have an operator combining in some way or the other two numbers or two entities, two symbols, then as long as we have two of them, then our operation is a binary operation. And of course, this is your operator. So your regular addition takes place making use of two operands or two numbers. You're adding two numbers, then that addition operation is a binary operation. The same is true for your multiplication because there are two operands, which makes it a binary operation. Bi meaning two, and when we say binary, we are talking about the two operands, as we have also in subtraction and division. However, in this formative stage of your binary operation, we define binary operations in a way that will benefit us, or just for flexibility, just for introducing the topic at this early stage, because binary operations will be a serious thing when you start to advance mathematics at the university level. So this binary operation here is defined as A asterisk B. These two are the operands, and how are they combined? It is defined right here in this algebraic statement, meaning 2 times A minus 5 times B. So here we have 2 times something minus 5 times something. It's as simple as that. But at this early level, all we are doing is defining a rule for your binary operation, and you are required to carry it out. Now, examiners want to extract more marks from you, therefore they might be a little bit more innovative, like in this problem in which we are also considering commutativity as a part of the problem, and of course in this one we are solving a quadratic equation. But for the intents and purposes of binary operation, we just have the definition of the operation, and we are required to just apply the operands to it, irrespective of what they are. What number, what letter, what expression. So in this particular case, it is defined as 2A minus 5B. A, we are going to just say A asterisk B is equal to 2A minus 5B. 2 times something minus 5 times something. The first one goes there, the second one goes there. So all that we have there, 2 3s, which is 6, minus 5 4s, 20. So we have a negative 14 right there. So that's what we have for the first one. So I'm taking a look. Okay. Well, the sound is there because we have been checking on the sound, and it is said that the sound is very low. So I'm seeing other responders, and I'm going to tell if it is also very low by their account of everything. So let us give them some chance. So what we have here is 3 asterisk 4 is equal to negative 40 because of how this one is executed, how it is applied with the numbers that we have here, according to how it is defined here. Now we're going to have 3 asterisk 4 asterisk 1. What does that mean? Now we define a binary operation as something taking place on 2 operands. But now what we have here, we have 1, 2, 3 operands. So that might be in defiance of what I said before, but it's not really, because the operation is taking place on these 2. And then on the result, we're going to use the result to operate on this. It's just like your addition. If you have 3 plus 5 plus 7, this does not prevent the addition from being a binary operation or a binary operator, because we have 3 plus 5, we'll have to do that, then when we get 8, we add 7 to it. Right? So, at any stage of the game, we can only apply addition to 2 operands. So we cannot apply addition to 3 operands at a time. We can do it for 3 operands, but we'll have to do it 2 at a time. So we'll have to add these 2. When we get the result, we'll have 8 plus 7, which we are just adding another 2. So at every stage of the game, we are just adding 2. So we are still working with binary operation. At this point, we have 3 asterisk 4 asterisk 1. Now this might be a little bit daunting in appearance, but do not forget that we have 3 asterisk 4 already, and we know the result. So we are going to replace this with negative 14, and then we are going to have asterisk 1. And we are going to use the same rule that we have there. 2 times the first minus 5 times the second. So we'll have there 2 times the first, which is negative 14, and 5 times 1. Right there, the second is 1. And we'll just finish this up. Negative 28 minus 5. And that is equal to negative 33. What about this one? The binary operation is given or defined by using a triangle operation in this case. Alright. Alright, so the sound, according to the respondents that mention anything about the sound, is the sound is clear. One is saying it's low, one is saying it's not too bad. So I am really attributing that to the devices that the students are using. So what I'll do, I'll say thank you very much. Right, in that group. Right. So we have another one. A, and the operator on this case is a triangle. In this case is a triangle. And what this is defined as is equal to the square root of something plus 4 times something. So it's the square root of the first one plus 4 times the second one. This really should be a common D that we have there. Right. So all we need to do, 4 times, well, we have the 4 times B, and then we have the A. But we have A is the first, B is the second, and we have them in the same order here. That means 1 asterisk 2 should be 1 times 4 times 2. And that is going to give us the square root of 4 twos, 8 plus 1, which is 9. So that is going to give us the square root of 9. Alright. The square root of 9 will go there. And surely, as soon as we see the square root of 9, we are going to say that the square root of 9 is equal to 3. But I need to bring it to your awareness. I know that I've done that before, but I'm going to remind you that each number has 2 square roots. So there are 2 of them, a positive 3 and a negative 3. So if you use your calculator and you do 3 squared, you're going to get 9. If you do this on your calculator, negative 3 squared, you're going to get negative 9. Why? Because by doing this, only the 3 is squared and the negative is not squared. So what we'll have to do is put that in brackets. When we do that, then we'll have a negative 3 multiplied by a negative 3. Negative times negative is positive, so that's a positive 9. So if we just put negative 3 squared without the bracket, then only the 3 will be squared. And that will not be the square of negative 3. So we need to be mindful that if we are asked the square root of any number, of course, there are 2 square roots. Now, as far as commutativity is concerned, to say that it is commutative, sorry about that. We are looking at commutativity. What do we mean by being commutative? To commute means to go back and forth. And in mathematics, commutativity has to do with the order in which operations are carried out. Well, the order of the operands in this particular case. So, if we have, for example, 3 plus 4, that is equal to 7. If we have 4 plus 3, that is equal to 7. And this is true irrespective of what 2 numbers we use. Therefore, we say that addition is commutative because the order in which we add numbers does not affect the result. Multiplication is true also. 15, 5 times 3 is equal to 15. So that's true for multiplication. It is therefore true for multiplication, but it is not true for subtraction, in which 4 minus 3 is equal to 1 and 3 minus 4 is equal to negative 1. So, addition is commutative, multiplication is commutative, subtraction is not commutative, and of course, if we do for division, we realize that division also is not commutative. So in this particular case, we want to know if this is commutative, meaning that the order in which we have the operands does not matter. So if we change the order of the operands and the result is the same, then we know that the operator is commutative. And proof in mathematics is really a sophisticated thing, because if we show one single case in which it works, it is not proof enough to say that it is commutative. Unless that single case would have been a general case. But if we can find one case in which the order does matter, meaning that when we change the order the result is not the same, then it is enough to say that it is not commutative. Because commutativity requires that it is true in every single case. So when you start to go to a higher level to do stuff like working in your Cape, and when you get to the university, you will see that proof is a little bit more sophisticated than it appears to be at this level. But if we can show that there is at least one case in which it is not true, then it is enough to disprove. It is enough to disprove. However, when we are using a proof, we have to use a general case, and it has to be the same in every single case. Alright, so commutativity, is this commutative? Let's see. We have 1 asterisk 2. Now we're going to be, it's not that, it's triangle. So 2 triangle 1, which is equal to the square root of 2 plus 4 times 1. As we have it defined there, the first plus 4 times the second. And what do we have here? The square root of 6. So here we have the square root of 9. Now it is the square root of 6. When we change them around, the result is not the same. Therefore, it is not commutative. So this triangle operation is not commutative. I'm going to put it below. So it's not commutative because when you change it around, it is not the same. Now, what about this one? 5, I'm going to change, that has to be cross here. So we're going to change that to the cross here, like what we have there. So it is m cross here, L, is equal to m squared minus Lm. Therefore, when we're doing this, we should put a template that looks like it. Something times something. Right. So 5 is the first. We'll go here and there. So 5 goes there, 5 goes there. And of course, L, which is the second one, will go right here, and in the same order. So what we have is 5 squared, which is 25, minus 15, and that is equal to 10. No problem. Now our examiners imagine that they can be a little bit innovative by giving us G as an unknown to combine with 4 with that same operator that we have there, and that is equal to 3. So let us do that. So we are going to have something squared minus something times something is equal to negative 3. And that we need to solve in the end because it's going to be an equation in which G is the unknown. So we're going to have G squared there, we are going to have G there, and 4 will go there. Do not forget that at the 2 ends we are going to have, the first one. First one operating at 2 ends. And then the other one is this one. So what we have there is G squared minus 4G. And of course, since we're going to be solving a quadratic equation, we're going to have that in trinomial form on the left-hand side. So we're going to eliminate this negative 3 by addition. So we're going to have a plus 3 there equals 0. And what do we say? Trinomial G squared minus 4G plus 3 is equal to 0. And we're going to say what 2 numbers do we know that multiply to give a positive 3, but when we add them, we get a negative 4. So that's going to be G minus 1, G minus 3. Here we'll never attempt to teach you to solve a quadratic equation. And we're not going to teach you to factorize a trinomial. We have thousands of problems on my YouTube channel and otherwise on the internet factorizing a trinomial. So what do we have? G is equal to positive 1 or positive 3. So those are your values of G. And our operation here is a spiral in this particular case. So we have the spiral A, spiral B. And some people might call it a different name, but it's the same symbol and you know how to write it. In an examination, no one will ask you what that symbol is. It's just that you need to just use it in the binary operation. Alright, let's go. So, we're going to have a template that looks like it. This operation. So that's equal to, so in there we'll have something plus something all squared minus 2 times something times something. So there's a template that looks like it. And of course, as usual, well, according to what we have here, and of course this should be a common A, we have what? A plus B, AB. So we'll have 3 plus 4, 3, 4. Simplifying that, instead of the bracket, we simply have 7 squared, and then here we'll have 2 times 3 times 4. So that seems to be 24, which is equal to 49 minus 24, which is equal to 25. So that's that for these binary operators, and we'll just give you 2 extras for you to have some more fun. We'll do that very quickly. Hopefully, I don't lose no contact with my book, so we can do some more. Ready? Yes, we have 2 more. We have, I'm going to use rectangle. So we're going to have A rectangle B is equal to A squared minus B. Well, that one is very simple. We just want to find 5 rectangle B, which is going to be equal to something squared minus something. And it's of course the first one. So B in this particular case is 2. So 5 squared minus 2. So that's going to give us 25 minus 2, which is equal to 23. There's nothing to it. And this one might be a little more, I'm going to use the asterisk again. AB minus B over A. I think that in this particular case, we have to be quite mindful that although we have AB, we have B over A in this particular case, in which the B is going ahead of the A. So, we are going to have the first part of it is 4 asterisk 8, and that is going to be equal to what? Something times something minus something over something. There's your template. And in the first case, it doesn't matter because it's AB, and that's for multiplication. But we'll still put them in the correct order, because multiplication is commutative, meaning that the order in which we multiply 2 numbers does not affect the result. So we could put the 4 and the 8 in front, it doesn't matter. And then it matters here that the second one goes first, 8 over 4. Why? Because division is not commutative. And I'm using the terms so that it resonates by the time we are through with this exercise. So that will be 32 minus 2. So that will give us 30. Then, on the other occasion, we'll have 2 asterisks with 4 asterisk 8. And what is that equal to? We know this part already, that 4 asterisk 8 is going to be equal to what? 30. And what do we know? That we have 1 multiplied by the other, then we have 1 over the other. Do not forget that although the first one, the order does not matter, and we're going to be putting them in the correct order nonetheless, 2 times 30, that in the second case, it is what? B first and then A next. So the second one will go first. And what do we get? 2 times 30, 60, minus 15. So we have there 45 for our answer. So your binary operation is by no means a difficult thing, but I appreciate the fact that the examiners will give us maybe a quadratic equation to be included, or for us to demonstrate knowledge of our basic arithmetic by asking us if one of the operations is commutative or not. And we are just required to apply that knowledge of our basic arithmetic for as it pertains to commutativity right there. So that is answering your request, because this topic was requested by someone on my YouTube channel, and my students did not do this topic before, so I've taken what? 1 stone after those 2 birds. So it is for my students who did not work with binary operations, and also for someone on my YouTube channel who requested this topic in binary operation. I hope that it was very informative, very useful, and that your intents and purposes for requesting the topic